Now that we have named our 5 logical connectives and we can translate English statements into our logical symbols, our next task is to be able to decide whether these combined statements are true or false. So recall, any mathematical statement has 2 possible values. A statement can either be true or it can be false, but never both. We can now specify the meaning of the logical connectives by listing the true-false values for every possible case. So let's start where there is a case with just one statement, P. We know that P is either true or false. And we want to consider the negation of P, or not P. Well, these true-false values are as you would expect. If P is true, the negation of that would be something that's false. And if P was false, the negation of that would be true. Each of the other logical connectives involves combining 2 statements, P and Q, and we need to consider all possible cases of true-false values. So the first case could be when P and Q are both true. We could also have the case where P is true and Q is false. We could also have P false and Q true. And finally, we have the case where P and Q are both false. These 4 scenarios represent every possible combination of true-false values for P and Q. So let's consider the statement P and Q. So when is that statement true? P and Q is true when P is true and Q is true. So we need both statements to be true for the combination to be true. That only happens in row 1. So we get a true value for row 1, but because Q is false in row 2, P is false in row 3, and in row 4 both are false, the combination of those things must be false. So think of your and symbol as both. We need both statements to be true for P and Q to be true. Now let's consider P or Q. The statement P or Q is true if either P is true or Q is true. So for this statement, we just need one. We just need one of P or Q to be true. That would happen in row 1, row 2, and row 3, but nothing is true in row 4, so we cannot have a true statement in row 4. But all of the other rows are true because at least one of P or Q is true. Our next connective is the if and only if connective. And remember that the if and only if is an arrow that can be read in both directions. So what we're looking for here is that the true-false values agree on both sides of this double arrow. So that's going to happen in row 1 where both values are true. And it's going to happen in row 4 where both values are false. Because those true-false values agree, we can say that the if and only if statement is true in row 1 and row 4. But I don't have an agreement in row 2 and row 3 between P and Q, so that combined statement must be false in those rows. Finally, we have the implication symbol. P implies Q. So this one's a bit interesting. Remember, another way to read this symbol is to say if P, then Q. So think about it this way. If P is true, then Q follows from there. But what if P is false? Can anything follow from a false statement? And no, the answer is no. So in this case, when the if part is false, we call the statement vacuously true. We can't conclude anything from a false statement, so we can't say that it's false. And if it's not false, then it must be true. There's only 2 options. So I know that's a little tricky. We'll talk about it more when we're together in class, but just know that whenever the if part of an implication is false, the P implies Q is always true, no matter what Q is. It doesn't matter whether Q is true or false. These are vacuously true when P is false. And if P is true and Q is true, the implication would be true. And if P is true and the then part Q is false, then the implication is false. So again, just make sure you're writing down each of these truth tables because they will serve as definitions for each of the 5 logical connectives. All right, now that we have these 5 connectives defined, we can use them to construct truth tables for any mathematical statement that we want. So let's take a look in this example at the negation of P implies Q. So I have 2 letters here, P and Q, that I'm going to want to put in my table. So what other columns do I need to include in my table? Well, I've got P implies Q that I'll definitely need. And then I want to negate P implies Q. So those are the 2 columns I'll need. P implies Q, and then we'll negate that column to get our final answer. All right, anytime we have 2 different statements with truth values, we'll set it up the same way every time. True, true, false, false for P, and then true, false for Q. Again, that combination represents every possible scenario of true, false values. And then we go from left to right. So our next column, P implies Q, we have that definition defined on a previous slide. P implies Q is true, false, true, true. And then our final answer, we want to negate P implies Q. So true will become false, false will become true, and we can fill in the rest of the column. So our final answer are the values in this final column. See if you can do this on your own. Construct a truth table for the statement not P implies not Q. So you'll need to think about what columns to include in your truth table and in what order. And try this one out and we can check your answer in our next class.